I know you're impressed with my originality. I try. Mr. C2. What? Come on, join, man. How come I'm not able to join? Mr. D. You join Mr. Is this the extra long version? Yeah, I better start new notes, eh? Look at that. That's too long. Okay, new notes. Template. Okay, so we are. What am I doing? Am I recording this? Well, someone's got their volume on. That's you. Hello. Okay, it's off. Good. Let's start with a prayer. Father, Son, Holy Spirit, we'll pray. Or again, my friend's mom passed away. Pray for her and the family. Pray. Glory be to the Father, to the Son, and to the Holy Spirit, as it was in the beginning, is now, and ever shall be, world without end. Amen. We're going to go over page 38 in the workbook. Let's look at that. Whoa. Okay, so I'll do it for you. What's the y-intercept for the graph shown above? What does it represent is what they're asking. What's the value and what does it represent? I think they tell you what it represents, but let's just. Okay, so hello? Okay, so the unit is the giveaway. It's meters per second. I'm going to represent the velocity as v. It's speed, but we need to start getting a little bit more precise now. Velocity is speed with a direction, as long as you don't turn around. Okay, so this starts at about this is 10 meters per second, and this is 20. Starts in between at about 15. Time. We call that the initial velocity. Sometimes you'll see what is the slope of the graph. So this you choose any 2 points. Okay, I'm not going to go through the calculation with you, but any 2 points that are convenient. should know how to do that by now. To find the rise and to find the run. So in this case, it's the slope. The slope is rise over run, which works out to be 4 plus 4. Two sig figs is fine for now. Looks like it's limited by the time, so it would be 2 sig figs. Okay, we're not finished. We need the units. For the units, we go to the units on the y-axis, which are meters per second. And then we divide that by the units on the x-axis, which are seconds. And now that's sloppy. That is the unit. That's correct, but that's a sloppy way of writing it. The simpler way of writing is simply meters per second squared. It's an abbreviation. That is the unit. It's important you realize it's no longer meters per second because now we're dealing with a different quantity or a different concept. This is the acceleration. It's no longer the velocity. It's how quickly the velocity changes. And so the unit is different. Different unit. Okay, we're no longer dealing with a D versus T graph. It's now a V versus T graph. Okay. So we call that acceleration. The slope and make sure you're clear on this, on a V versus T, not D versus T. We can call whatever we want. The name that we've used is something that's familiar to everyone, and that's acceleration. Whether it's positive or negative. Okay, if it's negative and you're moving forward, it's what we usually call deceleration. But in physics, we use the term acceleration to refer to both positive or negative. Yeah. So positive in this case, slope is positive. What's happening to the velocity? You're going from, again, I'm just making these numbers up. You're starting here at 15, and then you're moving up the slope here, blah, 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 blah. What's happening to your velocity? You're increasing. You're going from 15 to 20 to 30 to 40 to 50. 50 is your final point here. So positive slope means you're increasing your velocity. You're accelerating. What you usually refer to as accelerating. C. What property of the moving object does the slope represent? I just mentioned it, acceleration. With units of meters per second squared. This, by the way, is not wrong. If you wrote it like this, it's not wrong. It's just sloppy. It's not the abbreviated form. Okay, write the equation for the graph using symbols. So it has to be of this form. It's a line, so it's going to be of this form. It's going to look similar to this. Where this is the y-intercept. We already have that. Let's fill that in. I'll start filling in different letters and numbers in a second. We already did this. This we did in part A. That was here. That's your initial speed. It's where the line intercepts the y-axis right here, 15. Let's include units. The unit of the y-intercept is the unit on the y-axis, which is meters per second. Okay, let's fill in some of these. Let's fill in y and x. and then I'll do m. So this, we used to say it was d. It's no longer d, it's v. Make sure it pertains to what you're plotting. No longer d that we're plotting, v. I'll come back to the slope. M is the slope. X now takes on, instead of x, we're going to use whatever we plot along the x-axis, which is similar to what we did for the d versus t. It's t. Everything remains the same. I'm putting the units in red. Okay, last step. Fill in the value for the slope, which we got. We just calculated it here. Well, I stated it here. That's the slope. I would put positive just to make sure. On a test, I'm a little bit more forgiving. If you just put 4, I would understand it or interpret it as +4. But when you're doing assignments, try to be a little more careful. With unit of meters per second squared, I'll highlight it in red. Times t plus 15 units in red. That might be the way for us to do it. Maybe change colors if you can when you're writing the equation. Put the units in a different color. Okay. Number 2. Read that to yourself, and I'm going to change the equation because it's not the way we usually use it. I'm going to be a little bit more precise and put little arrows on top. The arrows remind you, you have to remember to include a positive or negative value. Okay, here's what I'm going to make use of. Objects, it's similar to moving right and left, except now we're moving up or down. Objects moving down have a negative velocity. Okay? And the opposite, if it's moving up, it's going to have a positive velocity. Okay? So keep that in mind. One more point here. Okay? This is what happens when you drop an object. So I'm going to drop this object. You don't know that from experience, but it is accelerating. If it wasn't for air resistance, it would keep speeding up. So it's air resistance that actually prevents this object, if I were to drop it from, let's say, a high enough level, they would reach, or this would reach an escape velocity, not escape velocity, some sort of limit where it can't move any faster. Okay? So if it wasn't for air resistance, this book would keep speeding up. Ignore that. Okay? Objects accelerating downwards have a negative acceleration. Indicated obviously by negative sign. So we'll keep that in mind. I'm going to rewrite the equation they gave us. I'm going to put in front of the 5, I'm going to put a negative because this refers to an object moving down. And I'm going to change the units to red. And in this case, I'm going to write, instead of positive, I'm going to write negative. Okay? I'll give you a hint. Just look at the unit. The unit of this is the unit of acceleration. And we'll deal more with this later, but this number actually is the value that all objects accelerate in the ideal world. There wasn't any air resistance. The denser the object, the more they accelerate at this rate. So all objects, every object, accelerate downwards at negative. I'm going to get confused if I put, I'm going to separate negative 9.8. Okay? It's kind of redundant to say minus, but you need that minus there for the calculation. So all objects accelerate at this rate. In the ideal world, you're talking about floating feathers, well, then there's air resistance. But if it's a dense enough object, accelerates at negative 9.8 meters per second squared. Okay, before we continue further, I want you to look at this equation again. Try to write it out in terms of the initial velocity and acceleration. See if you can rewrite it in terms of variables. Get rid of the numbers. Yeah. I just mentioned this one here obviously is some sort of acceleration, right? So I can fill that in. Instead of writing negative 9.8, I'll just put A. Times T. Does that remind you of anything so far? No? Okay, here's a hint. Set this equal to 0 at time 0. What do you get? Set T is equal to 0. What does VF equal? VF is equal to negative 5 plus 0, which is just negative 5. So what does that negative 5 represent? Good. It represents the speed or velocity when you start off, the initial velocity. So this here is your VI. What does that stand for? Represents the velocity at time 0. That's what we mean by initial velocity, the velocity at time 0. So I can rewrite this as is that familiar? Yeah, because we derived it previously. Go back to the previous notes. Okay. So it says at what speed was the ball initially thrown? We already figured that out. Initial means implies T is equal to 0. We just said it. So we can just call it VI. Okay, that's A. B, what was the acceleration of the ball? Again, it takes on this form here, where A is this. How do you know for certain that's the acceleration? The unit. Look at the unit. Meters per second squared. That's your giveaway. Must be acceleration because that's the unit for acceleration. How fast is the ball moving after 1.2 seconds? You take this equation. Just rewrite the equation. I'm kind of cheating. Okay, so it says t is equal to 1.2 seconds. Where are you going to plug that in? Yeah, just plug that into. Good. Plug it into t. I'm including all the units. You don't have to do that until you get to the very end, just so you know. Okay, before we calculate the numbers, what cancels out as far as units here? Which unit cancels out? Is the seconds on top? Is there a seconds on the bottom? Yeah. So one of these seconds cancels out. So you're left with just meters per second, which is what you want. You want your final unit to be meters per second because it's a velocity. Okay. So this works out to be, as in the answer, 17. What do I have to remember to put in front? Negative, negative. Two negatives add up to give a negative. It's negative because it's moving which direction? Yeah, moving down. Okay. Okay, one last derivation. Go back to, we're going to start off with this graph. Remember, we've got the following formulas so far. These are what we call kinematic equations. Let's just write the two out. What are they? Number one, what I just wrote out above. That one. That's the first one. How do we derive it? We derived it using a graph that looks like this. Look like this. What kind of acceleration does the slope represent? What time does it represent? Positive what acceleration? Good. Constant. Okay? So that's how we can apply this equation. Constant acceleration. 2, second equation. We derived this last day. It's this. You'll see it written different ways, but essentially it's this. In brackets, VI plus VF times T on the outside, half in front. Third equation. I'll add on to this in a second here. We're going to derive it. You should have read page 39. It's a different way of coming up with the same equation. Okay, so again, V versus T. This is your initial. This is your final point. So it represents here your final velocity there. Okay, with a slope of the slope is equal to the acceleration A. I'm going to call this time simply, instead of T final, I'll just call it T. This here is the rise, which is equal to VF minus VI. Let me make it a little more clear. This is the run, which I'll call T. It's TF minus TI, but we're going to simplify it. We're just going to call it T. The slope is equal to rise over run. So VF minus VI, that's the run or rise, and the run is T. Let's rearrange this. I want you to do it. Don't tell me. Rearrange it for T. Tell me what T is equal to. Solve it for T. Yeah. Solve it for T. Mm-hmm. Yeah. They're going to keep these little half arrows. Those are going to come into play later. Okay. This gets complicated, but this is how you get the equations. We're going to go back to this equation. Patience. You're going to insert this for T. Wait till you get to higher level physics.
Yeah, I know. It's going to be super long.
Okay. Okay. Now, you're going to help me complete it. Don't tell me, but multiply both sides by 2. And then multiply both sides by A. Don't tell me, but give it a try. I just multiply by 2. What cancels out on the right? Yeah, the 2 in the denominator. I'll just rewrite it. We'll do it one step at a time. I'll put this in brackets so it's more clear. I'm going to drop the little half arrows for now. I wrote them up to that point just to remind you they are there. We're going to put them back in at the end. Now multiply both sides by a. What happens to the a on the right? Okay, get in there. I'm just going to, these are just numbers. I can put them in any order I want. I'm going to put the a in the middle. Yeah, wait, almost done. Now multiply this through. Don't tell me, see what you get. And I'm going to help you. I'm going to rewrite this. This will help you. 1 sec. Nope. I'm going to put the VF first. It doesn't matter. They're just numbers. I'll help you out here in a moment, but see if you can get it. Foil, I think you call it, right?
Yeah.
What's that equal to? Figure that out first if you're not getting it.
Foil, it's, I don't know, x squared, xy, y.
Okay, so if you're not getting it, look at this. This is just algebra. What happens to the middle two terms?
Yeah.
You got a minus xy to plus xy. It's kind of like minus 1 plus 1. What's minus 1 plus 1?
Yeah.
Okay, let's go back to this. This is just like x. This is just like y. It's the same thing, or similar anyways. So what's my end result? X squared minus y squared. VF squared minus VI squared. One last step. Okay, add the VI squared to both sides. What happens on the right? Yeah, good. So you get, on the left, you get, on the right, you get this. I'll flip sides. Okay, I'm going to give you some really good news in a moment. Re-add the little vectors, and you don't have to put the little half arrows on top. I'll tell you why in a second. That is your third equation. I just switched sides.
Yeah.
Okay, so listen, before we go any further, under what condition did I derive this? It's this graph here. What can you tell me about the acceleration? What type of acceleration is it? Constant. Could be fast. I don't know. Could be quick. It's constant for sure. So listen, here's the good news. You need to be aware. What I just did is called a derivation. Called a derivation. Okay. You don't have to know how to derive it. You do need to know how to apply it. So we're going to focus more of our attention on that. However, why did I derive it? You can understand now why I keep on, first of all, emphasizing the importance of constants. It's constant acceleration because that's what we started with. Secondly, later on, if you go on to take higher level physics, you will be expected to derive equations. So you need to be aware of where it comes from. Okay, usually we start with graphs. You start with a graph, you have to maintain the same conditions at the end as you started with. Constant acceleration. Okay, so here, let's make a list. I'm going to add a fourth one because I'm going to save you pain. Really? Number one, just repeating myself. That's your first equation. Second equation. And this is in no particular order. It doesn't matter what order you list these. They are all derived under the constraint of constant acceleration. And the last one we just derived, the third one, and the last one, I'll just give it to you. And it's derived the same way. I'll save us time. Same graph. Those are the four kinematic equations. Okay, so if you can go back to your handout, the handout that I gave you, the last one, and turn to page 69. You're supposed to do 9 to 10. We'll go over that. You're supposed to have gone over that a while ago, so let's complete it. Okay. I don't think I did these. If I did, it's not going to hurt to go over it again. Yeah. Okay, let's look over the first one, 9A. I'll give you a moment to find it. It says a golf ball rolls up a hill. Yeah, it's the handout that I gave you, the last one. Yeah, page 69.
What? Oh, never mind.
Okay, we'll go through these together. It says a golf ball rolls up a hill. We're going to make a list. Yeah, watch. We're going to take going up the hill as positive velocity. Moving down the hill as negative. Okay, it says the ball starts going up the hill with a positive velocity of 2. So when we're making a list, that's how you do these problems. You use these equations by making a list. So your initial velocity, whatever is mentioned first, that's your initial velocity. Okay, it accelerates. I'm going to go fast here, so I'll probably skip putting the positive signs down. I do have to include the negatives, though. Notice the word acceleration. It accelerates. However, the negative means that the pull is down the hill. It's a deceleration. They say acceleration, but in terms of everyday usage, it's implying deceleration. Yeah, let's look. I'm just going to make a list first, and then you just plug it into the equation afterwards. So they give you a time, 2 seconds. And then the question is, what is the velocity at this time, at a later time? That's your final. That's your question. So the point of writing a list is to choose one of those 4 equations. So you go back here. Don't tell me. Go through this list. Tell me which equation contains all 4. The VI, A, T, and VF. I'll tell you in a second, but go through the list. It's not always going to be the first one. In this case, it's a little easy because we're starting off with the first one, but
What are the 4 things you need?
the equation should contain all the letters that are in the list. We call those letters variables. So which equation contains all four variables? V, A, T, and VF. First, second, third, etc. Which one? First one.
Yes.
Agreed? Okay, now we have to get particular. We're going to include our little half arrows, little arrows on top. That's to remind us that we have to take into account negative velocities and acceleration. So the VF is the question mark. So that we don't have to rearrange. It's already rearranged for us. VI, it's in our list. It's positive 2. I'm just going to put 2. I'm going to drop the unit. I need to save a little time here. The acceleration is negative. We'll put it in brackets. Negative 0.5. And the time, just go down the list. 2 seconds. Okay. So this works out to be 1. Positive. In your final answer, that's where it's important to include a sign, so I'm clear you understand. Positive means it's moving up still. It's slowed down. It's gone from, it started at 2. Now it's only going 1 meter per second, but it's still moving up. It's slowing down. B, I'll give you a hint. All these questions have only to do with one equation. It's this one. But later on, we're going to mix them up. Okay, so B, make a list. So now we've got the same initial. That doesn't change. Acceleration is the same. What changes is the time. So the time is now 6. And VF. Look at the list. Whoa, that's weird. Same as before. Same list as question 8. Same equation. Okay, you plug it in. If you haven't done this, plug it in now. I'm not worried about sig figs. We're just going to, if you're in doubt, just round to 2 or 3 is fine. So this works out to be 1 as well, except it's, yeah, which means now it's going downhill. It's turned around. Moving down. That's what the negative means, moving down the hill. Okay, I just did. I'm saving myself time. I already described the motion. 10. Bus is traveling. The very first velocity mentioned is initial. And I'm going to remember to change it to meters per second. Okay. In general, the unit is meters per second. Meters, seconds, and meters per second. Those are the standard units. So if in doubt, you can convert to those. How do you convert? Divide by 3.6. Divide by 3.6. I just, okay. And that gives you 8.3. What's the unit? Meters per second. Okay, accelerates. So I'm going down the list. Positive 3.5. Time 6.8. And then the question is, what's the final? Okay, in kilometers per hour, we can convert back later. We're going to get our answer in meters per second. And then we convert by multiplying. Okay, so same equation. How do I know to use this equation? Well, it's the only one that in this book or in this handout that we start off with. But in the future, you have to go through the list. Check that the equation that you think works contains all the letters. And it does, so I can use it. So VI is 8.3, acceleration is 3.5, time is 6.8. 7 is 21, 10, 18. So I got 32.1 positive meters per second. How do you go from that to kilometers per hour? Yeah, multiply by 3.6. So that's 116. So 2 or 3 sig figs is fine. Put it in scientific notation if you want. 2 sig figs, 1.2. If it's bigger than 100, that's the general rule. Put it in scientific notation. Okay, I asked you to do number 11 too, so last one. Okay, car accelerates from rest. Okay, let's make a list. You're looking for words that help you find values from rest. Implies initial velocity is 0. That's your key phrase there. Acceleration, I'm just going to make up a nice list. VI is 0. Acceleration is given. It's 5.5. And it's positive. There's no mention of being positive, so you can assume it's positive. There's no mention of it. It's positive. How long will it be required? How long? What's that a code phrase for? Yeah, time. Time, question mark. Reach, to reach a speed, that is the final. That's your list. Which equation? Yeah, because it contains all 4. Later on, this becomes more difficult because you'll have a shuffling of the questions, and there's a possibility of the question using one of those 4. Okay, go through the list. VI is 0. Okay, 0. Acceleration is 5.5. The time, we don't know it. The VF is 28. Okay, so this simplifies to 28 is equal to 5.5 over t. How do you rearrange for that? How are you going to solve for the time? Okay, you're solving for this. You're multiplying 5.5 by the t. You want to isolate for t. You do the opposite. Divide the 5.5 out. Okay, so t works out to be 5.1 seconds. Don't forget the units. T is always positive. Okay, alternatively, you could have done it this way. Up to you. the same way, except you're solving for the variable first. Solve for t. Rearrange that for t. You remember how to do that? Vf minus Vi is equal to At. Vf minus Vi. Same thing, except you solve for the letters first. You get the same answer. You can use either one. You need to get used to this. There's a reason why we learned how to rearrange equations. You need to work your way up to that. But if you want to start with this, just plugging in numbers, then rearranging, that's fine. Okay. So turn to page 72 in the handout. I want you to do exactly what I did. Make a list. You're going to do 13 to 16. Make a list. Also, next page, 74. Sorry, I didn't write the page down. 60, 72. Ah. '72 and 74. Just 17 and 19. That's your homework. Now, here's the thing. I'm going to go through these with you next day. I won't be here Tuesday. I have a recording for you. After the recording, after I've gone over them with you, I'm going to then give you an assignment out of the workbook. Yeah? Oh, that's right.
And Wednesday.
I forgot I'm on the retreat with you. What I'm thinking. This doesn't end. Wait. Don't laugh. You still have to do this.
Yeah. Like, so on Thursday then?
I need an assignment. That's the problem. Shh. No, the problem is I'm short. Wait, don't say anything. This is the problem. I'm gone Tuesday, Wednesday, and then Thursday I'll probably be here. Yes. So I will see you Thursday, right?
Yeah.
So here's the thing. The assignment, if you want to get a head start, will be from your workbook. Page 40. It's simple. It's using the same. This is an assignment. I'll post it ahead of time. It is due. This is the important part. So I'll see you Thursday. It's going to be due Thursday night. It's pretty simple. It's 4 equations. I need the marks. Due. No, yours is going to be due Thursday.
Thursday night.
Thursday night.
After class.
Yeah. This is a nightmare. Well, I'm going to be with you on Tuesday for the retreat. Wednesday, I got to go to a funeral. Where are we going Tuesday? Richmond?
All like the Buddhists have one, all the different religions.
That should be interesting. Okay, good. Is that clear, everyone? I'll post the notes later. I know that was pretty long class, right? No? One sec. I know. I didn't get around to the whatchamacallits. I can't even do it at lunch because I've got duty. So